My name is Cedric. We're going to start with just a quick experiment. So I'm going to play a note on the keyboard, and I want everyone to hum the sound that they hear. Okay? We ready? Are we excited about this? Yeah. All right. So more on that later. Who am I? My name is, I'm a consultant. I'm a founder of a consulting company. I'm an occasional speaker and an occasional author of books. I work at a company called Spantree, and I also do a lot of stuff with music. I'm really into synthesizers and MIDI and all that stuff. I also used to compose music, and so I got a little bit into music theory. There are some people in the audience that are probably way better at music theory than I am, so please feel free to correct me after. And I'm also a Spotify addict. I really love music, and I really love playlists. They're a passion of mine. And I'm also a recovering DJ. There'll be more on that later on. So this is a talk about music theory. And that was Mozart back there a slide ago. This is, is anyone familiar with this cartoon? All right, we're gonna make use of fair use copyright provisions, and we're gonna watch a little bit of, this is called Math Magic Land. It was a cartoon put out by Disney in the 50s to sort of get children interested in math.
Let's go to ancient Greece, to the time of Pythagoras, the master egghead of them all.
Pythagoras?
The father of mathematics and music.
Mathematics and music?
Ah, you'll find mathematics in the darndest places. Watch. First, we'll need a string. Stretch it good and tight, plunk it. Now divide in half. Plunk again. You see? It's the same tone, one octave higher. Now divide the next section. And the next. Pythagoras discovered the octave had a ratio of 2 to 1. With simple fractions, he got this. And from this harmony in numbers developed the musical scale of today.
Okay, so this was probably like one of my favorite cartoons as a child. I loved it so much, this was actually my AOL screen name in high school. It's Pythagoras spelled backwards. I also, when I put out some music, I actually went under the pseudonym of Pythagoras, so that's a picture of a high school me, and the album is called Pathology. More on that later also. Remember when I said I was a recovering DJ? That was like 2-3 minutes ago. So let's talk about college. So I had a brief career as a classical music composer. I was like sort of making music with MIDI, and it sounded something like this. And I had a slightly longer career as just like a general MIDI musician, like kind of playing around with synthesizers. Is everyone familiar with MIDI, by the way? I figured the Strange Loop crowd would be. It's basically the protocol that musical, like electronic musical instruments use to communicate with each other. So I was really into that also, and I made music that sounded like this. But then college happened, and no one was really feeling the classical music, and no one was really feeling the MIDI. I wanted to make friends, and so I got into DJing, because parties, and I hopefully didn't look like this person, but I used to do a lot of mashups, and this was one of my more popular mashups called Beyonce Rockin' Beats.
Can you keep up, baby boy? Make me lose my breath, bring me noise, make me lose my breath, hit me hard, make me lose my...
Anyway, you get the point. What the hell was that? That was a combination of Destiny's Child, Lose My Breath, and then it was playing over Chemical Brothers' Block Rockin' Beats. So how did that work? Harmonics. Remember Pythagoras? He had that whole ratio thing, so that ratio informs what music sounds good together. And there's this YouTuber, or I'm sorry, and in this case, the Destiny's Child was in a key of D flat major, and Block Rockin' Beats was in a flat of B flat minor. Now you would think, okay, those are different those are different keys, but it turns out that they actually use the same notes. They're what's called a complementary key, so you can actually layer those two things on top of each other. And it happens that B flat is a major sixth of D flat, which means that they share the same notes. And why does this matter? Because the brain likes to do math, but not too much of it. So when we were talking about those ratios before, when we're hearing different notes or different chords, the simpler the ratios are between the notes, the more pleasing it is to the ear. And there's a whole science behind it. There's this YouTuber named Adam Neely. Is anyone familiar with him? Yeah, all right. We got an Adam Neely fan. So he put a video online that sort of explained harmonics and how the ear processes sound. And I'm going to share a little bit of that because he does a better job of explaining it than I can in a compressed amount of time.
When the sound of the clips hits your inner ear, a structure called the basilar membrane will vibrate in sympathy with the total number of clips hitting it per second. Tiny hair cells in the inner ear will convert that acoustic information into electrical impulses that the brain can then interpret, just the same way that a microphone will pick up sound waves to be either amplified or recorded. What happens next, I think, is pretty incredible and also not that well understood. Our ears can do math really quickly.
I'm afraid we need to use math.
Let's take these two sine waves. One vibrates at 520 times per second and the other vibrates at 650 times per second. Your ear automatically calculates the ratio between the two of them as 5:4. This is the interval of a major third. Because 5 against 4 is a simple ratio with simple integers, our ear accepts it as a pleasing sound. Our ears automatically do what our conscious brains might have to labor over, quickly calculate ratios between two separate pitches. And boy, can they do it quickly. Thousands of notes per second can be processed by the brain with the right sort of math behind it.
So what does that have to do with Beyonce?
Well, maybe the answer lies in the harmonic series. The harmonic series, also known as the overtone series, is based upon simple multiples of a fundamental. So if your fundamental is 100 hertz, the second harmonic will be 200 hertz. The third harmonic will be 300 hertz. Just take whatever the frequency of a note is, multiply it by a number, and then you get that number harmonic. So easy, even a musician can do it. We hear all of the different harmonics as different pitches and intervals in relationship back to the root. Our brains process the differences between harmonics as musical intervals. The ratios between two of them create a harmonic interval. For example, the distance between the fifth harmonic and the fourth harmonic creates a 5:4 ratio, or the ratio of a major third that we heard earlier. Major thirds are in our system of Western harmony, but other intervals aren't, like the distance between the seventh harmonic and the fourth harmonic.
So remember we were talking about keys. The notes that were included in both of those songs were basically the same. It's just that you had a different, what's called a root note. And when you're making playlists, when you're a DJ on stage, like mixing records together, like the compatibility of those notes has a lot to do with how musically pleasing it is. And I wanted to take that further and see if we could teach computers a little bit of these rules. And so we'll get into that later. By the way, I forgot to mention this at the top of the talk. It's generally discouraged to use your phones. I'm going to ask a participant to use their phone to find a publicly available Spotify playlist that we're going to optimize together by the end of this talk. So feel free to look something up and I'll search for it and we'll find it together and run some algorithms on it. When we were talking about keys, D flat major is the relative minor, B flat is the relative minor of D flat major. So what that indicates is that these notes those notes actually are the same as the notes on the other scale, the B flat. I swear to God I practiced that. I did. Last night, the night before, demo gods are never kind. Okay, so let's see this on a keyboard as we just did. While we're over there, remember that experiment we did at the beginning of the talk? Remember where we were humming a note together. Well, let's try that again. But this time I'm going to manipulate the note. So this was the note that we heard. Can we hum it again? Okay. So how many notes do you think you were actually hearing there? One? So with the overtone series, what we were listening to is these drawbars here are actually impacting the other pitches that are played at the same time to add richness. So I'm going to slowly subtract those tones away. So we're hearing all those notes together, but because they were complementary to each other, because they had very simple ratios, they didn't really sound dissonant. They didn't sound displeasing to the ear. But this is also a talk about playlists. Now that we have some of the music theory background behind us, let's talk about how this could apply to making our Spotify playlists sound better. So what matters musically to a playlist? There's a lot of things that matter emotionally to a playlist, like sentimentality and that sort of thing. But from my perspective, there's three key components. There's tone, and that's the stuff that we were talking about a second ago. There's timing, or timming, and that has to do with the tempo and the rhythm and the time signature of a song. And then there's also timbre, and timbre is actually all of the relative ratios of all those tones that we heard. So the timbre of an organ is very different from the timbre of a guitar because the overtones are fundamentally a different structure. And that can make an impact on the pleasingness to the ear as well. So let's talk about tone. Are there any DJs in the room? All right. Have you seen the Camelot Scale before? No? Okay. So the Camelot Scale is this graph that's used a lot in what's called harmonic mixing when you're trying to play two records at the same time and not have them sort of stomp on each other as far as sound. So what this represents is each key has a fifth up or a fifth down, so 5 notes on its scale up. And if you transition from, let's say, E major to B major, that's a pleasing sound. However, if I went very far on the scale, if I went from an E major to a D flat major, or even worse, like an E major to a B flat minor, because those are so far apart, it will actually sound like a train wreck. It will sound very uncomfortable. And so oftentimes when DJs are putting sets together, they will try to figure out how they can either stay in the same key for a while or jump to just one over on the Camelot scale, either left or right or down. So basically what they're doing is pathfinding. They're trying to find a path from one song to another by making as small a move as possible on this Camelot scale to get from one key to another. And it turns out that a lot of DJs get paid a lot of money to do this. I wanted to apply this to my own sort of like mixtape making as I started getting into taking non-dance songs and sort of putting them into playlist form. And so this is an example of a playlist transition that I created using this technique, analyzing the songs 4 keys and then sort of sequencing. So there's a little bit of a drone in the background, but what you're hearing there is basically 2 songs that are texturally very, very different, but because they match up on the key, it works. And so this was an exciting thing to be able to do. back in the day when I actually owned the music and I had the MP3s, but nowadays people don't really own their media anymore. A lot of the media is in the cloud. Most people are listening to music on Spotify or Apple Music and less likely to be able to, if I shared a playlist, they would be less likely to play it. So the good news, though, is that playlists are everywhere. They're pervasive now. There's even PhD theses being written about playlists and the sort of abundance of playlists in the new cloud media economy. But we can't do fancy tricks like this where we're layering a bunch of records on top of each other. In Spotify, we can't play more than one song at a time. But what can we do? Well, we can reorder the tracks. So based on those music theory notes from earlier, we can create a rule-based system that allows us to figure out the best way to structure songs together from one to another. So is anyone familiar with Ryoichi Sakamoto? One person. All right, cool. So Ryoichi Sakamoto is a Japanese composer. He worked with David Bowie back in the 80s, and he's a very particular individual. And when he went to this restaurant that he frequented in New York, he was really annoyed with the playlist, and so he actually secretly programmed the playlist using his musical brain for 3 years. And then the New York Times found out about it, and they wrote this whole piece about it. It turns out that there's actually a lot that you can do when you're applying these rules. And so this is a talk about discrete optimization. Discrete optimization, per Wikipedia, is about finding a best solution in a sea of solutions. And with a playlist, if you have a 100-song playlist, there are millions of possibilities for how to order those songs properly. And so the TLDR on that is that you have a finite number of possible solutions. That's the discrete component of it. But you're also searching those options to find one that closely matches a set of rules. So what are our rules in playlist building? The song should play exactly once. That's sort of table stakes. You shouldn't have repeats. Some song transitions to be to songs in the same key. And other songs should be to adjacent keys on the Camelot Scale. You don't want to listen to a playlist that's all one key. And so these are all rules that we're going to use to optimize our playlists today. And song transitions should also avoid drastic tempo changes or timbre changes as well. You want to gradually shift people from one mood into another, generally. But all the songs are in the cloud. So this is a talk about API integration. So who is familiar with Spotify's web API? It's actually quite dope, isn't it? It's pretty awesome. So they, when I sought to create a playlist optimizer, I was expecting that I'd have to go download all this media and build my own analyzers, basically doing tonal analysis on the MP3s themselves. But it turns out Spotify actually purchased a company a few years back in 2014 called the Echo Nest. It was a project out of MIT, and they had actually automated a lot of this analysis, and they exposed all this data about their songs over the API. So what we end up with is every single song that's in Spotify right now, I can make an API call and get the key indicator, the mode, the tempo, and then a bunch of other properties, like they have a danceability property, an energy property, an acousticness property, and we can weave all of these into our planning system. So these two lines indicate that this is a song that's in D major. The key 2 indicates the root note, and then 1 indicates a major mode. But we also get a lot of other helpful stuff for optimization as well. So like if we wanted to optimize and pay attention to the time signature, we could do that. If we wanted to make sure that we weren't jumping around between tempos, we could factor that in as well. So we have the data, but how do we actually optimize for the playlist? So there's this really cool and sort of underappreciated, in my opinion, technology called Opticsplanet. It's an open source library for the JVM. And what it allows you to do is write a series of business rules. So basically, like when this condition happens, penalize the solution, and then it applies a bunch of heuristics to try to find solutions that break as few rules as possible. So the steps for setting this up, first we model our domain. In this case, a track is one of our domain objects, and the track will have relationships to artists, and it will have albums, and it will have a duration, and there's an explicit flag, so you can filter things out if you don't want things that are explicit. And then you also have this notion of a track. So in addition to just what are called the facts, the data about the tracks, we also want to find some way to represent the relationship between the tracks. So this track is playing after this other track. So then we have what's called a planning entity and an anchor. So we have to specify where the playlist needs to start. That's one of the sort of non-negotiable pieces of the way that this optimization system works. But then what you're setting up as the thing that changes is for every other track in the playlist, it's going to randomly select tracks that could be played before, and then over time it will actually create a linked list of these tracks together, and it will look for the solutions that violate the fewest rules. And we'll go into the mechanics of rules in a second as well. So this is what this looks like in practice. So in our case, when we're creating a playlist, we start with one song, and we're going to shift the relationships between each playlist track basically by just assigning a pointer. And Opticsplanet is going to effectively make those sorts of experiments thousands of times a second, evaluating whether or not the playlist improved. The first playlist track remains as the anchor, and we're using this planning variable as sort of our independent variables in the experiment. So during optimization, we're experimenting with alternative planning variables to each planning entity. And then we have a solution that's basically the completed playlist. So this is all of the tracks, their relationship to each other. And we also have what's called a score. And the score is the thing that we're going to be trying to get as close to 0 as possible. Every time you're playing a track that is in a key that's not complementary, you basically penalize the planning system by a point. In addition to that, we also have facts. So if we wanted to write a rule to say don't play the same artist like 2 times in a row, you have data on that. You also have genre information that's available through the Spotify API that's for some reason attached to artists. So you could say, for example, I want to clump all my jazz songs together. I want to spread them out. And finally, we have a score, which is used to track the quality of the working solution. And so you have different levels, so different constraints will take different priorities. So for example, if I'm playing the same song twice, that's considered a hard constraint, meaning that this should just not physically exist. And then a soft constraint is like, ideally, I would like for all the keys to sort of match up, but maybe that's not feasible. So that's what's referred to as a soft constraint. So scores have slots, and you can assign basically weights. So in this case, like this solution has resolved all the hard constraints. That's at 0. And there's still some outstanding issues with soft constraints, and so there's some negative weights there. So no feasibility issues, but there are some things that are suboptimals, and so the system is going to seek to continue to improve those things. So now let's write some rules. This is an example of a rules using the Drools language, which is it's a pattern matching system for the JVM. So you'll notice this looks a lot like SQL. What you're expressing here is basically a pattern. When I have a track and the track is pointing to a different track, and in this case we're trying to make sure that the song is playing only once. When the track is playing somewhere else, then penalize. So basically, you have this score holder add hard constraint match down at the bottom. What this is doing is it's saying adjust the score, the overall score of the solution by -1, and then these things will be summed up to try to basically try to get as close as possible to a 0 score. So we look for a track that has a previous track defined. We check to see if there's another track in the solution that points to that same track. And then anytime that happens, we add a hard constraint with a penalty of 1. And so this can happen several times in a solution. And what ends up happening when we're writing this syntax, it gets compiled into a data structure that's called a ready tree, R-E-T-E. And effectively, what this data structure allows us to do is as new information comes in, like tracks are being reassigned, it can quickly reason through the impact that that might have on the score and only recalculate the things that need to be recalculated. And so it's an extremely efficient system as well. But what about key rules? Does anyone know who this is? This is Francis Scott Key. He's going to be our key ambassador for the key discussions coming up. So we might want to figure out, basically, if I have 2 songs that are playing back to back, what is the distance in the key on a Camelot scale? And to do that, we add what's called a shadow variable. That shadow variable is going to allow us to execute some code that calculates the difference based on the set of known sort of relationships between those keys. And then we have a listener, and the listener's effectively going to take, and this is a lot of code, this listener is effectively going to look for those updates and figure out how far away they are on the Camelot scale and update that value in real time. So this is the part that lets us know when something is happening. So anytime something changes in the rules, in the facts, these methods will be called, and then this will dispatch basically this imperative method that will calculate the distance. And so we're doing just a little bit of math there. And then finally, this is kind of an interesting component of the system as well. Anytime you change a variable, you need to inform the rules engine that you're about to change a variable so they can figure out what it might need to react to. And so we're basically informing it that this variable is about to change, we change it, and then we say we're done changing it, and then it will be able to evaluate the impact of just that one discrete change. So now that we've done all the heavy lifting, and this is in Kotlin, our key rule is very simple. All we need to do is just look for a playlist track, and if it has a key distance that's greater than 0, basically take the square of that distance and penalize the score. So things that are further apart are going to be exponentially penalized in this system. So since most playlists contain songs in more than one key, the score will never be 0, but we're trying to get it to as close to 0 as possible. And we could also add rules to basically say that we don't want to play more than 4 songs in the same key. So break up the tension every once in a while by introducing something new. So how does it do that? Is anyone familiar with n-queens? The n-queens system. So it's often used, like you'll see it referenced in Prolog. Effectively what you're trying to do is if you have a chessboard, you're trying to move all the queens to a position where they can no longer attack each other. And so this is an interesting problem for an optimization system to solve because the rules are very simple. But what the optimization system is doing is it's picking a piece, it's moving it to a random location, and then it's seeing if it made the score better. So in this first position, basically all the queens can attack each other. When I move this piece to a different position, now this queen can no longer attack this queen can no longer attack this queen, but these queens can still attack each other, and these queens can still attack each other. So you have some constraint violations, but you've reduced the amount. And over time, you can continue moving the queens until you found an optimal solution. So you're just searching through a finite solution space, and that one rule is basically dictating the quality of the solution. So the sequence of moves also impact the next viable move as well. And so one of the things that's really interesting about these sorts of systems is that it will be intelligent about the likelihood that a random move is going to yield a better change. So it'll realize that I just moved this queen before, and it made the score worse. And the last 5 times I've moved this queen, it's made the score worse. So that queen's probably in an optimal position, and I'm going to move on to another part of the problem space. So Optiplaner uses random series of moves and a whole bunch of different strategies for selecting those moves. And it's always trying to select the subset of moves that will make the score better. So how does this apply to playlists? Let's watch a solver in action. So this is from the code base for this playlist optimizer that I've written. And so what's happening is we start by basically loading in all the data. And very quickly, it's looking through a batch of moves, and it's trying to determine whether the score got better or worse. And so you'll see these scores here. They should be going down, but occasionally they'll go up to avoid local optimums, or local maximum. So what the hell was that? Let's dissect a specific log line. So in this particular log line, we are selecting a move of moving this song behind this other song. And when we've selected that, it will basically impact the score, and the Optiplaner system will try to resolve that impact and keep track of when it had the best scores and try to return to those if it gets off track. So before it does that, it also just tries to place all the songs anywhere in the playlist. And so what will often happen is it will select the best songs at the beginning of the playlist, and then eventually you'll get into a difficult situation at the end where you don't have a high selection of available songs. And so after the construction heuristic is complete, where you can't undo a move, then you move on to a local search, which allows you to basically undo moves and backtrack just the same as you would if you were playing a game of like hot and cold. So if we just do the construction heuristic, we'll hit a local optimum, meaning that the solution will seem as good as possible, but because a lot of the decisions have been set in stone, we won't be able to backtrack from that. And so the local search resolves that. And there's a whole bunch of different strategies that the local search system will use. And after a long while, we'll end up with an optimized solution. So for most playlists, it's important to note that we'll never get a perfect solution. There are often competing rules that will make it impossible to find an absolutely perfect playlist. But one of the nice things about this system also is that it will tell you what's suboptimal. So if we have a rule that's being violated, it'll actually tell you what songs are in violation of that rule. And then you can manually resolve those if you want to, just with your own musical insights. So let's see it in action. I had a goal of being able to launch this tool before the talk, and I'm happy to say I got this up about an hour ago. So this is Spotfire. I'll go ahead and log out so you get the full user experience. So if you go to Spotfire.io, you can log into Spotify. Immediately it'll show your own playlist. And you can see I've been testing this a lot because you'll see the same playlist over and over again. But did anyone get a chance to pull up a Spotify playlist for testing? The Obama 2019 playlist. All right. Let's see if we can find it. This one, summer playlist? All right. Okay, so it's 44 tracks. So what's going to happen, and I'll get into the mechanics of the system in a little bit, we're going to pull the data down from the Spotify API. I spent a lot of time on this progress bar. You don't think about those details until the night before your talk. And then now that we've loaded the data in, we have this sitting basically in a Postgres database now. We're going to serialize it into a zip file in Amazon S3, and then we're going to load an optimizer in AWS Lambda, and we'll actually be able to see some logs, hopefully, of what's going on under the cover. So when I click Optimize, there's going to be a router bug, because I discovered that a few minutes before the talk. While we're doing that, we can take a look at our logs. Oh. There we go. All right. And you can actually start to see some of the output here as well. So maybe we'll do a split screen. I'll bump up the font a little bit there. This is what happens when you have a lot of iTerm tabs. So you'll see here on the left, this is like the web interface telling you what's going on. So what's happening is it's moving all these songs around, trying to find a better fit based on these musical rules. And you'll actually see how many rules are left being violated. So there's a rule saying the key distance should be kept to a minimum. If I'm not in a complementary key, then basically there'll be a violation thrown. And so there are 18 instances in the current working solution for that violation. And you'll see that there's also a -42 score, meaning that in certain cases, the key distance is more than 1. And so we're actually taking the squares of those to discourage like super, super large jumps. And then we have another rule saying that we should avoid playing an artist that was recently played, and so there are 28 violations of that as well. But I've set that as a lower priority, so that will then not result in as drastic of an issue. We want to make sure that the keys are compatible first. What's nice about this system is you can continue adding rules, and the performance remains mostly the same. So if we go to this Spotfire playlist now, we're done solving. I'll skip the explicit song. So we should hear songs that are now in a complementary key. So that just jumped up a fifth. And then we're up another fifth. And so these transitions are meant to be more pleasing to the ear based on those ratios that we discussed. What's really exciting about this system is that if you have a different preference, if you actually don't care about key compatibility, but let's say you want to optimize for playing artists with the same last name back to back, all you have to do is just change your rules, and everything magically works. And oh, by the way, I forgot to mention at the top of the talk, this whole project is open source. There's actually 3 projects on GitHub right now that were launched in parallel to this system. So there's the API that uses Prisma and Postgres and Node and TypeScript, Apollo Server, Nexus, and the Spotify Node API, because I like a lot of technologies. So that's basically doing all the heavy lifting of pulling in the data and managing the flow of data from the user experience to the solver. There's the website, which is serving up the user experience that's using Gatsby, and TypeScript again, React components, and a router, the Apollo client. So we're actually doing some dynamic rendering inside of a statically rendered website. And we're using Auth and Jot tokens to do the authentication to Spotify, and Netlify for building and hosting. And on the back end for the solver, we're actually running this in AWS Lambda, so we're dispatching from the API to a Lambda so that each optimization process gets its own discrete set of resources. So for that, we're using Kotlin, Optiplanar, Joules, AWS Lambda. And this system is live as of this morning. There are some bugs that I'll be squashing this afternoon, but feel free to check it out. So I wanted to thank Strangeloop. Both the audience and the organizers. I've been going to this conference for almost a decade now. And I also wanted to thank the Spantree crew. So especially Justin, Madi, Sebastian, and Eli. They've all helped me with this project and with this talk with specific contributions. And then the Spotify and EchoNest teams and some great open source projects as well. So feel free to check it out, issue pull requests, issue issues on this system, and feel free to use Spotfire, just Spotfire.io. Thank you.